everyone, I am Snigdha Bharadwaj, Assistant Professor, ITS College of Pharmacy. I welcome you all in my session. So, in this session we are going to discuss about various pharmacokinetic parameters and their estimations. So, let us get started. So, we have been discussing in our earlier sessions about clearance and the various models of clearance. So, now we again have a look about clearance and their basic estimations. So, now drug clearance is a pharmacokinetic term for describing drug elimination from the body without identifying the mechanism of the process. So, basically every organ has its own ability to eliminate the drug from it by its own mechanism. So, basically it is unknown, and to identify the drug eliminated, we generally use this term clearance. So, once the drug is absorbed in the blood and other body fluids, after reaching to systemic circulation and body fluids, it will start eliminating from the system. So, to observe these elimination concentration of drug in urine and in other different bile and through other elimination processes, we generally take it the clearances value to identify this drug elimination or drug excretion. So, instead of describing the drug elimination rate in terms of amount of drug removed per unit time, drug clearance is defined as a fixed volume of fluid containing the drug cleared of drug per unit time. The units of clearance are volume per time, that is ml per minute, liter per hour. So, accordingly we can take the units as per our need. So, for example, if the clearance or total clearance we say of penicillin is 15 ml per minute in a patient, and penicillin has volume of distribution of 12 liters, right. 15 ml per minute in a patient. So, total clearance of penicillin is 15 ml per minute, and patient penicillin has volume of distribution of 12 liters. Then from the clearance definition, 15 ml of the 12 liter will be cleared of drug per minute. That is it. So, if we are saying that the drug clearance is defined as the fixed volume of fluid containing the drug cleared of drug per unit time, the units are ml per minute. So, if we say that penicillin is 50 ml per minute and the total body fluid containing the drug fixed volume of fluid is 12 liter, then we can say that 15 ml of the 12 liter will be cleared of drug per minute. So, this is how we calculate the clearance for any particular drug. Alternatively, CLT, total clearance, may be defined as the rate of drug elimination divided by plasma drug concentration, right. So, rate of elimination divided by plasma drug concentration. So, here CLT is equal to elimination rate divided by plasma concentration, or we can also say it CP. So, CLT is equal to, if we talk that it is taking at time at different time intervals, that means we are taking the time value. So, drug elimination by dt is equal to ml per minute, and this is CP. So, elimination rate will be like dE by dt Cp CLT. So, if we simplify this equation to get elimination rate, the equation will become this. So, just as the elimination rate constant K represents just as the elimination rate constant. So, elimination rate constant is represented by K. The sum of all the rate constant for drug elimination including CLT is the sum total of all clearance processes in the body, including clearance through the kidney, renal clearance, it is also say lung and liver hepatic clearance. So, basically I repeat, just as the elimination rate constant represent the sum of total of all the rate constant for all drug elimination, including excretion and biotransformation. So, CLT is the sum total of all the clearances processes in the body, including clearance through kidney, lung and liver. So, just in case, constant rate is a sum of your total body drug elimination constants like excretion constant, right. So, elimination basically your constant of excretion and biotransformation, okay, transformation. So, likewise CLT is the total, we can say hepatic, renal and others like lungs and all. So, this is the sum of CLT is the sum of total of the clearance processes in body, including clearance through the kidney, renal clearance, lung and liver also known as hepatic clearance, right. So, this is how we calculate clearance. So, comparison of drug excretion methods. Renal clearance may be measured without regard to physiologic mechanism. So, basically we do not find out the mechanism of drug clearance from the body organ, body fluids. We just identify the amount of drug eliminated or cleared at per unit of time of the drug from the body fluids. So, it involves from a physiologic viewpoint. However, renal clearance may be considered as a ratio of sum of glomerular filtration and active secretion rates less the reabsorption rate divided by plasma drug concentration. So, when we discuss about physiologic viewpoint, that the clearance how it is getting cleared. So, renal clearance involves three different biologic functions like filtration rate, secretion rate, reabsorption rate. So, divided by blood plasma concentration. So, the formula will be like CLR filtration rate, secretion rate, filtration rate and secretion rate minus reabsorption rate. So, this is very important, reabsorption, because from the kidney what is getting filtered and secreted, once again it may be reabsorbed. So, that is also taken into consideration, it is very important, right, process. So, if we skip this process, that means we are not getting the exact clearance values from kidney. So, the actual renal clearance of a drug is not generally obtained by direct measurement, right. So, the actual renal clearance of a drug is not generally obtained by direct method, because several biologic if we talk in biologic viewpoints. So, several processes are involved. So, for one by one we will discuss. So, filtration only, if we consider filtration only, in glomerular filtration is the sole process, if glomerular filtration is the sole process for drug excretion and no drug is reabsorbed, then the amount of drug filtered at any time t will always be Cp GFR, glomerular filtration rate. Likewise, so I repeat, if glomerular filtration is the sole only process for drug excretion and no drug is reabsorbed, if we consider that no reabsorption process is there and no drug is getting reabsorbed from the kidney, that means it is a sole process. Glomerular filtration is the sole process of drug clearance. So, in this case, then the amount of drug filtered at any time t will always be Cp GFR. That means, we are taking the concentration of drug in related to GFR only. Likewise, if the CLR of the drug is by glomerular filtration only. So, if we are saying that the filtration drug excretion process is only glomerular filtration rate, no drug is getting reabsorbed. So, likewise, if the CLR of the drug is by glomerular filtration only, as in the case of insulin, then clearance is equal to GFR. So, in this in this equation only GFR will be there, no reabsorption is there. So, only this value will be taken for calculations or identifying calculation for clearance, right. So, in case of insulin, then clearance GFR, otherwise CLR represents all the processes by which the drug is cleared through the kidney. That means, only the GFR will be responsible for drug clearance, we are identifying it, right. So, including any combination of filtration, reabsorption and active secretion. So, we generally consider it the whole sole process of filtration, reabsorption and active secretion. So, we took the it is a common process of clearance, renal clearance. So, the equation will be like du by dt Ke Vd Cp compartments. If we consider it as a compartment, du by dt is equal to CLR Cp physiologic, right. From the above equations, Ke Vd Cp is equal to CLR Cp, and by simplifying it, Ke CLR by Vd. So, this is how we usually compare the equations to understand different physiologic variation and processes. So, filtration and reabsorption, that was about filtration only. Now, if we consider reabsorption also in during renal clearance for a drug with a reabsorption fraction of Fr, basically Fr is the fraction of drug, reabsorption fraction of drug Fr. The drug excretion rate is reduced and equation the below equation is restarted equation in a new equation. Like if we say that drug is getting reabsorbed, that this equation will be followed again. This equation will be followed again, including reabsorption rate. So, the equation will become that d du CLR Cp, what here V Vd Cp CLR Cp, yeah, that du dt CLR Cp. So, physiologically if we consider no reabsorptions taking place, only glomerular filtration rate or single sole processes happening here, but if we consider reabsorption as well, so the equation will become, the earlier equation will become du by dt is equal to CLR 1 minus Fr. Fr represents the reabsorption fraction, drug reabsorption fraction, and then plasma concentration. So, equation, the right side of the equation of this equation and that equations, this equation, yes, this is the first equation, and after that the last equation, the right side of equation 1 and 4th indicates that the first order rate constant in the compartment model is equivalent to CLR. So, basically we are just solving the derivation. So, by simplifying and taking the values, equivalent values, we can say that first order rate constant in compartment model, as you can see it is written here, the compartment. So, the right hand side option is Ke Vd Cp. So, here if we take this CLR 1 F minus Fr Cp. So, left side is same. So, right side is comparable with both the equations. So, rate constant is affected by reabsorption fraction and the GFR, because these two parameters generally remain constant. The general absorption of a first order elimination process, general adoption of the first order elimination process to describe renal drug excretion is a reasonable approach. Basically, what we are trying to say in this, that if we compare the compartment modeling and physiologic considering reabsorption processes, that the right side of both the equation will be comparable and rate constant basically affected by the reabsorption fraction and the GFR. So, both the processes plays an important role, because these two parameters generally remain constant. So, it is basically remain constant, and the general adoption of first order elimination process to describe renal drug excretion is a reasonable approach. So, basically we just follow the first order kinetics drug for drug excretion to identify renal drug excretion. Basically we usually take up, and both the GFR and fractionable part equations is remain constant. Now, if we discuss that without considering that reabsorption, and we are taking filtration and active secretions, and then the equation will be, for a drug that is primarily filtered and secreted with negligible reabsorption, the overall excretion rate will exceed GFR, right. For a drug, I repeat, for a drug that is primarily filtered and secreted with negligible reabsorption. That means, in this condition or in this case, we are not considering reabsorption process to be taken place, right. So, we are just thinking that only assuming basically that only filtration and active secretion is there, no reabsorption phase will be occurred for drug excretion. The overall excretion rate will exceed GFR at low drug plasma concentration. Active secretion is not saturated, and the drug is excreted by filtration and active secretion at high concentration. The percentage of drug excreted by active secretion decreases due to saturation. So, these are physiologic viewpoints that they are trying to say, if we are not considering reabsorption, then the overall excretion rate will exceed GFR. So, overall normally we are considering GFR, but in this case we also consider active secretion, and now we can say that at low drug plasma concentration the excretion rate will be exceeding GFR, and active secretion is not saturated, and the drug is excreted by filtration and active secretion at high concentration, the percentage of drug excreted decreases due to saturation. So, if we are taking into consideration only glomerular filtration rate, that means the drug concentration excretion will be exceeding and as compared to GFR, and when we are taking GFR filtration as well as active secretion into consideration, we are saying that drug excreted by active secretion decreases due to saturation, right. So, clearance decreases because excretion rate decreases. So, when excretion rate GFR we are taking into consideration, we are saying that drug excretion is high, that means clearance is high, and active secretion plus filtration. So, the it decreases and CL will be also decreases. So, this is how we can build up a relationship between various physiological processes. So, clearance decreases because the total excretion rate, the drug increases to the point where it is approximately equal to the filtration rate. So, clearance decreases because the total excretion rate of the drug increases. So, totally basically if we see that if we talk about GFR, so clearance rate or excretion rate is higher than the GFR, and when we consider active secretion only, so the it is showing decrease in clearance. So, if we sum up both the values, so we will find that the total excretion rate of drug to the point is equal to basically filtration rate, right. So, model independent methods basically. So, clearance rates may also be estimated by a single non-graphical calculation from knowledge of AUC 0 to infinite, the total amount of drug absorbed FDO, not basically at time 0 the total amount of drug absorbed, and the total amount of drug excreted in urine DU to infinite, right. So, for example, if a single IV bolus drug injection is given to a patient and the AUC 0 to infinite is obtained from the plasma drug concentration, plasma drug level time curve, the then total body clearance is estimated by CLT clearance D naught at time 0, AUC 0 to infinite. So, basically once again I would like to repeat this. Clearance rate may be also be estimated by single non-graphical calculation from the knowledge of AUC 0 to infinite, the total amount of drug absorbed. AUC basically is a total amount of drug absorbed and present in blood plasma, and the total amount of drug absorbed FD, and the total amount of drug excreted in urine DU to infinite. So, if a single IV bolus drug injection is given to a patient, a single, when we administered a drug through IV administration, bolus administration, the AUC to obtain plasma drug concentration, the total body clearance is estimated using this equation. And if the amount of total if the total amount of drug excreted in urine DU to infinite, so it has been obtained, then renal clearance is calculated using this equation CLT D naught to infinite AU C to 0 to infinite basically. So, or we can also represent this equation like CLT is equal to D naught to infinite divided by AUC naught to infinite. So, likewise we can present this equation. So, clearance can also be calculated from fitted parameters if the volume of distribution and elimination constants are known, volume of distribution and elimination constant, whereas in model independent approach we do not consider or assume these both parameters. Body clearance and renal clearance and hepatic clearance can be calculated according to following expressions. So, here if we use CLT total clearance KVD, CLR KEVD, CLH KMVD. So, total body clearance CLT is equal to the sum of renal clearance and hepatic clearance is based on the concept that the entire body acts as drug eliminating system. When we consider all these eliminating body organs and sum up the values, that means we are taking all the different organs into one and considering body as a eliminating system. So, equation will become CLT is equal to CLR plus CLH plus any other eliminating system we can also add up if in case we desire. So, by substitution of equation 6 these equation these equations by substituting. So, we can have this KVD is equal to KEVD KMVD. So, only dividing by VD on both sides and we will get equation K is equal to KE plus KM. So, total body clearance, it is estimated of dividing the rate of elimination by each organ with concentration of drug present. So, CLT is equal to CLH, CLR plus CL bile plus n number of elimination processes we will take into consideration. So, this is how we calculate total body clearances from the body systems. So, protein bound drugs are not eliminated by glomerular filtration. The bound drugs are usually excreted by active secretion following capacity limited kinetics. So, the determination of the clearance that separates the two component result in a hybrid clearance. So, basically for body protein clearances we generally adopt a hybrid clearance concept. There is no simple way to overcome this problem. Clearance value for a protein bound drug is therefore calculated using this equation: clearance, rate of unbound drug excretion and concentration of unbound drug in plasma. So, basically it is bound drug are usually excreted by active secretion. So, we generally take it into consideration. Plasma protein binding has very little effect on renal clearance or actively secreted drugs such as penicillin, but apart from this we always take this into consideration. So, these are references. I hope you understand the basic different insights I have given you about the clearance processes. I hope you understand this. So, we will be continuing this pharmacokinetic parameters session in our next session also. So, till then take care, stay safe. Thank you.